Welcome to another episode of Measurements and Measurable. This is the second half of the part 2 where we are discussing experimental errors. In the first half, we arrived at this formulae, or rather, we discussed this formulae. And we told you that the big question is, if we are measuring an unknown object, how do we know the true value beforehand? Well, we cannot. However, we are dealing with random errors. So if you repeat the measurement sometimes, the error will be positive and sometime it will be negative. Suppose we repeat the measurement 10 times and obtain repeat respectively x1, x2 up to x10. We define mean value as x bar equal to x1 plus x2 up to x10 divided by 10. This is just a simple averaging formula that you know. Average value is equivalent to mean value. They are same. It is reasonable to expect, at least for a large number of repetition, that random error will be positive half of the times and negative half for the rest. So, in the mean or average value, when we add up all these values, the errors will cancel each other out. The mean value or the average value is then can be used as true value. However, it is still prone to some uncertainty as the result never cancels out exactly. Generally, for n measurements, mean x is defined as x1 plus x2 up to xn divided by n. I'm sorry for the typo. See, this is a more formal definition where we use this summation symbol. This is intuitive and perhaps most of you are familiar with this. Absolute error for the ith measurement is delta xi equal to x min minus xi. Relative error in the ith measurement is then delta xi by x min minus xi by x min. Notice we have just replaced xt by x min. For the ith measurement, the deviation is defined as xi minus x min. Notice that deviation can be positive or negative. That is why for a large number of measurement, if we add up deviations, we will often get 0 if the errors are truly random. So it's not a good quantity to deal with. To avoid this problem, we define something called standard deviation, which is always positive. And this is the formula for standard deviation. It is customary to define standard deviation as sigma, but you can denote it with any other symbol. This is an even better formula for standard deviation. Now, for a low value of n, it is far better to work with the second definition. For large value, however, both definitions converge. At this point, you may find it odd that I am just mentioning some formula heuristically without any justification at all. The trouble is, a full logically consistent theory comes from statistics, which is beyond the scope of the present discussion. However, although you have to take my word for now, you can be rest assured that the rationale behind the formulas are well known, and most of them can be derived from basic assumptions. Finally, the standard deviation of mean, sigma x mean, is equal to sigma x by root over of n, where n is the number of data. So at the end, you can quote the result as x min plus minus sigma x. Now, at the beginning of the measurement lecture, I told you that we can talk about correctness of measurement in a quantitative way. Now we are in a position to have a test of that. Statistics tells us that there is a 95% chance of the true value of the measurement to be found within the interval x min plus minus 1.96 sigma x. The chances that the true value lies within x min plus minus 3 sigma x is more than 99%. However, all this is correct if the number of observation is large. In practice, these are reasonably accurate for at least n greater than 8. Most of the time, your experiment will consist of measurements of more than one quantity. Probably, you will use some of the formula to combine these measurements and find the final result. So, we need rules regarding the propagation of errors when more than one uncertain values are added, subtracted, divided, or multiplied. I briefly mentioned the rules of propagation of simple error, which is now called SE. Adding or subtracting a constant does not change simple error. Multiplying or dividing by a constant multiplies or divides the simple error by the same amount. For sums and differences, add the squares of the simple errors together and then take root. For products and ratios, squares of relative errors are added together and root is taken, then it is multiplied by either product or ratio. The simple error of the average of n equally precise number is equal to the simple error of the individual numbers divided by the square root of n. So these are the common rules you will be using. Remember, it is for simple errors and for measurements which are independent of one another. For dependent measurement, we have to deal with them differently. The rules I gave you should help you in experiments you will be performing in near future. As I mentioned, a proper study of error analysis involves statistics. It is fascinating subject itself, but it will probably be an overkill at this point. Rather, I would emphasize the need and application of error analysis once again. Suppose we are faced with a problem like the one said to have been solved by Archimedes. We are asked to find out whether a crown is made up of 18 karat gold as claimed or cheaper alloy. The density of the gold is 15.5 gram per centimeter cube and that of the alloy is 13.8 gram per centimeter cube. So two experts are summoned. The first expert, George, might make a quick measurement of P, that is the density, and report that his best estimate for density is 15 and that it is almost certainly lies between 13.5 gram per centimeter cube and 16.5 gram per centimeter cube. Our second expert, Martha, might take a little longer and then report a best estimate of 13.9 gram per centimeter cube and a probable range of 13.7 to 14.1 gram per centimeter cube. Now let us understand the situation graphically. The trouble is that George's estimate has an error so large that it fails to distinguish between the alloy and the gold. This is the graphical representation. See, this is George's error. And it is so broad that both gold and alloy lie within its range. So George cannot definitely say whether it is made up of gold or alloy. Now, consider Martha's error. This is tiny. So Martha can definitely say whether it is an alloy or gold. In this case, it's the alloy. So that's one of the importance of the precision and one of the importance to have an estimate of error in your final result. In the applied sciences, for example, the engineers designing a power plant must know the characteristics of materials and fuels they plan to use. The manufacturer of a pocket calculator must know the properties of its various electronic components. In each case, somebody must measure the required parameters and having measured them must establish their reliability, which requires actually error analysis. Engineers concerned with the safety of aeroplanes, trains, or cars must understand the uncertainties in drivers' reaction times, in braking distances, and in a host of other variables. Failure to carry out error analysis can lead to accidents. We have seen 3 or 4 people, even in some cases 5 or 6 people riding a bike designed to carry only 2. That is also possible as the design parameters generally make room for that much of tolerance. We still need to discuss on writing your results in a scientific way. That's in the final part of the series, part 3. Till then, here are some ideas for your own research. Wikipedia and YouTube are excellent sources of free information. Search critical terms and concepts to get a more detailed overview. If you have access to PCs and it has a spreadsheet program like MS Excel, Microsoft Excel, you can make many of these analyses with ease. Check YouTube to guide you through. Most of the scientific calculators have built-in functions to calculate mean and standard deviation. If you have one, you should learn how to use it. If you do not have a manual for your calculator, you can always Google for it. Learn about regression. Next time you do an experiment, try to make use of some ideas you learned here. At least have a scale, that is ruler, and try to measure a few lengths. Then try to analyze the precision of your measurement. Till the next part, goodbye.